Welcome back to geometry. We want to take a look at section 18, looking at the second half of it. So we want to just consider the following theorem. If we have two parallelograms that have a common base and have sides opposite that base contained in the same line, then they have equal area. So to get a nice visualization of what we're talking about here, we have a common base, okay, and then the side opposite that is in the same line. So if we have a common base, and then we have the opposite sides. This side is in the line, this side is in the line. So the rectangles or the parallelograms that we're looking at here are A, B, C, D, and B, E, F, C. I think I'm looking forward to Christmas looking at the color arrangements here, red and green. If you're colorblind, I'm sorry. On the left is green, and on the right is red. Or maybe red is on the left and green is on the right. I don't know. Anyway, so we have two parallelograms and they have a common base and the opposite sides are in the same line. So that's what we're talking about here. And what we're saying is that these two parallelograms have the same area. Awesome. So we're going to consider the first case. The second case is left for an exercise. So case one, where the lines do not overlap. Okay, the reason that this makes a difference is because the method by which we prove this, we consider the areas of the regions that are created. So we have 4 regions where we could label them region 1, region 2, region 3, and tiny region 4. So we can prove this. The idea is that they have common area 2, and then in order for them to be the same area, area 1 and area 3 would have to be the same. So we have to find some way to relate areas 1 and 3. And what we can do is we can consider the fact that the triangle ABE is congruent to the triangle DCF, right? We have AB is congruent to DC because of the parallelogram. So the opposite sides are congruent. And then we have BE is congruent to CF, again for the same reason, because of theorem 17.3, where it says the opposite sides of a parallelogram are congruent. So that gives us side, and what we'd like to have, actually, we don't even use that, but we use that those sides are parallel, actually. So yeah, we'll just keep going. Anyway, so we could use side, and then, but we can't do side angle. We'd have to do side angle side. So we'd have to show that this angle and that angle are congruent, which we would get from the fact that these two lines are parallel and this is a transversal, but also that these two lines are parallel and this is a transversal. And we will use that idea. So we can get that these two triangles are the same, and once we have that, then this area and that area, 1 plus 4 and 3 plus 4 are the same based on what we looked at in the previous video, that if two polygons are congruent, then they have the same area. So we'll use that. That's the idea. Once we have that those two triangles are the same, then when we subtract that quantity, then we get 1 and 3 are the same, and 1 plus 2 is equal to 3 plus 2, and we're essentially done. Okay, so that's the goal. That's what we're going to do in this proof. So again, this is case 1. So, of course, we start by the givens. So A, B, C, D is a parallelogram. And right, A, B, C, D is a parallelogram, and E, B, C, F is a parallelogram. Excellent. Those are what is given. So since they're both parallelograms, I know that EB is parallel to FC and that AB is parallel to DC. So EB is parallel to FC and AB is parallel to DC. And that's just the definition of parallelogram, or part of the definition anyway. So 3. All right, from there, we have some angle congruences. And we get them because EB is parallel to FC and AB is parallel to DC. So if we look at AB is parallel to DC and EB is parallel to FC, then we can get the angle created right here. We'll call that angle 1. This angle, if we were to use that, let's see here, if we were to use that AB is congruent to DC, we would get that that is congruent to this angle. And then if we were to use that this angle, or sorry, that BE and CF are parallel, this angle is congruent to this angle, which we will call angle 2. So we get that 1 and 2 are congruent, and both of those are a result from the converse of the corresponding angles theorem, right? They're parallel, so corresponding angles are congruent. So there's a couple different ways to get there anyway. All right. So we have that angle 1 is congruent to angle 2. But we can do similarly for essentially the same reasons. Let's see here. I wanted to say that it was this angle and that angle. Well, yeah, we'll call it those anyway. In the proof that I was given, I think that they didn't give good labelings for angle 3 and 4. So we have that angle 3 is congruent to angle 4. And that is because of the converse of the corresponding angle corollary. Excellent. Of course, EF is a transversal of parallel lines BE and CF. So those corresponding angles would be congruent. So that's how we get that one. That one's a little bit more immediate and obvious. All right. So next step is to observe the congruent sides. So we have this angle and this angle are congruent to this angle and this angle. So that would give us angle, angle, and angle, angle. So we want AB is congruent to DC, so we can have angle, angle, side is congruent to angle, angle, side. So AB is congruent to DC, and we get that by theorem 17.3, in particular part B of that theorem. Excellent. So this gives us angles and sides. So that way here in our next step, we can say that triangle ABE is congruent to triangle DCF. ABE is congruent to DCF, and that's given by angle, angle, side, where the first angle is actually 3 and 4, so angle 3 and 4. Second angle is 1 and 2, and then the side is AB and DC. So that would be 3B for our first angle, 3A for our second angle, and then 4 for the side. Once we have that the triangles are congruent, we get that desired sameness or equality in their areas. So the area of triangle ABE is equal to the area of triangle DCF. And this is by the area congruence postulate. Right, that would be on the previous video, previous page, area congruence postulate, this guy right here. Two polygons are congruent, they have the same area. Two polygons are congruent, they have the same area. All right, now let's talk about the areas that we're actually interested in of the parallelograms, and then a restatement of what the areas of the triangles are. So we have the area of the parallelogram ABCD is equal to, well, ABCD, that's area 1 plus area 2. That's area 1 plus area 2. So keep in mind, right, these areas 1, 2, 3, 4, 1, 2, 3, and 4 are areas, right? I'm not labeling parallelograms. I'm not labeling triangles with those. I'm labeling areas, right? This is an area. That's a number. So the area is equal to this area plus that area. The area of parallelogram EBCF is given by 3 plus 2, or 2 plus 3. Excellent. And the area of triangle ABE is equal to ABE. So we look at areas 1 and 4. And then the area of triangle DCF is given by areas 3 and 4. DCF 3 and 4. Excellent. And all of these are because of the area addition postulate. And these are two polygonal regions that are unioned to give a new region. This region union that region gives our triangle. This region union that region gives our triangle. This region union that region gives our parallelogram. This region union that region gives us this parallelogram. All right. Our next step is to recognize that we have some equivalencies here. We have that the area of this triangle is equal to the area of that triangle, but we have what those areas are given as. So 1 plus 4, area 1 plus area 4, must be equal to area 3 plus area 4. And that's just by the transitive property of equality. Well, we can subtract area 4 from each side to get that 1 is equal to 3. So we did some algebra there. And then we can go ahead and add area 2 to both of those, right? Because 1 is equal to 3 now. 1 is equal to 3. And if we add 2 to both sides, that gives us the area of this parallelogram and the area of that parallelogram, showing that they're equal. So 1 plus 2 is equal to 2 plus 3. And of course, that's the addition property of equality. If you just said algebra, of course, that would be fine as well. And then what do these represent? Well, these represent the areas of A, B, C, D, the parallelogram, and the area of E, E, C, F, the other parallelogram. And that's again by the transitive property of equality. And that's it. Right? We wanted to show that the two areas are the same, and we were able to do that. And that's it for this section. So if you have any questions, feel free to let me know. Of course, stop by during my office hours, schedule an appointment, send me an email. For those of you that are in class, stop by in class. I'll see you guys soon.